Electromagnetic spectrum. Woo! Each of these are the waves right here. Wavelength is the distance between each peak. Okay, you can see here, these have a longer wavelength than these. Now this is just energy. We're demonstrating energy. So these are shorter wavelengths. This is medium, very long over here. So gamma rays are very, very short. In fact, they're 10 to the negative 5 in nanometers. So remember nanometers, billionth of a meter. All right, then we have X-rays. And everybody, if you've ever had to get an X-ray fractured in your bones or whatever, they use very, very short wavelength energy. UV, ultraviolet light. This is from the sun, UV radiation from the sun, so shorter. Visible light then, so this is actually light we can see, is right here. Just this small section of the whole electromagnetic spectrum. Then we have infrared light, which is really like heat, which is a little longer wavelength than visible. So we can't see infrared, can't see UV. Birds, however, like Brutus, he can actually see, Brutus can actually see UV. He can see in this wavelength of light. Then you have microwaves, and then radio waves. Woo! Now, if we look at the visible light, so this is the only light we can see. This is the only section of the electromagnetic spectrum we can actually see. In the visible light is made up of colors. So, white light is made of different colors, and they range from very, very short wavelength to longer wavelengths. But in perspective, they're overall still have longer wavelengths than gamma rays, X-rays, and UV waves. So right here we're looking at, but in this part, some of these waves are longer than others. So the longer wavelengths are toward the red color. Shorter ones are toward blue. Now we have blue, we know now is a shorter wavelength than red. Okay, so these are the extremes here. So how do we use this if we're looking at stars? How do we know if stars are moving away from us or if they're moving toward us? Well, we're going to apply this now to the Doppler effect. When we look at waves, when we looked at the electromagnetic spectrum, this is what we looked at. It looked something like this. All right. Now, this is where people can get confused here. This is like a profile of the waves. So we're seeing like the side view of a wave, of the waves, the wavelengths. So if you were to look at a bird's eye view down at waves, like your more realistic perspective, they actually travel in all directions. So let's say this X is the police car as the siren blaring. The waves don't just travel in one direction, right? They're going in all directions, out, spreading out. Like you don't just hear the police car if it's behind you, you hear if it's over the side, if it's in front of you, it's on the other side. It travels in all directions. But when you see it look like this, if we're looking at the side view, so if I were to draw something, this would be like, here's the car then. So we have first wave, second wave, third. So this now shows the side view of these waves. So think of like in a pool. If you jump in a pool, when you jump, the waves spread out everywhere in a circle, like. So, but when we look at, generally when we're looking at the electromagnetic spectrum, we show the side view. So you can just keep in mind the whole perspective though, because the waves are spreading outwards in every direction. But we're not going to show every direction here. So most of the time when they show the wavelength, they're showing the profile. So they're showing just this part. Okay? Now, we're going to pretend we're going to look at this car from bird's eye view. So this is a police car, we're looking bird's eye. In other words, we're looking, here's, like if Brutus were looking down, how he would see it. That's why it's called bird's eye. All right? So here we have the car. Okay, there's our car. That's our police car. Wait, let's say this is us. We're standing here where the X is. The Doppler effect is a perceived change in the frequency of wavelength based on the position that the observer's in. So if this doesn't make sense, it will after I do this demonstration, I hope. So wavelength, generally if waves have shorter wavelength waves versus longer waves. Let's see. Okay, here we're looking at short wavelengths. Here we're looking at long wavelengths. And let's just look at maybe this section. These have higher frequency. This has a higher frequency. In other words, there are more of these waves produced, more frequent than the longer waves. So sometimes it's not just, we don't refer to it as just the wavelength, we just call it the frequency. Like high frequency, low frequency on the radio. I don't know if you guys, so higher frequency. In other words, they're happening more frequently, right? There's more of these short wavelength waves here than here. Here we have long ones, but there's only like one wave here. And here we have a few. So frequency is how often that wave comes. So frequency is the number of wavelengths, basically. The shorter the wavelengths, the higher the frequency. So now, let's look at, and the higher the pitch, so frequency kind of relates to the pitch, the sound. Higher frequency, waves are like slinky, real tight, like so like this, and the pitch is higher. The waves are like more like this, a lower frequency. Longer wavelengths, lower frequency. So here we are standing in the X here. Here's a car, police car, coming toward us. Now when it is standing still, that car's not, let's say first of all the car's not moving. Okay, so here we are standing where the X is. Here's the police car. These circles indicate the waves, sound waves spreading out from the police car because the siren is on, but the car is not moving. So the police car is not moving, but the siren is on. So it's creating waves going outward in all directions. If we were to show the waves here, then we would go like this, something like this. So if I did a profile version, it looks something like this. Okay, so let's say these should be about equal, these should be spread out equally. So there's no change in the frequency, there's no change in the wavelength. However, if the car is moving toward us, so if the police car is moving toward us, so now it's moving this way. Now the car is moving this direction. Okay, sound is still being produced in all directions. Okay, so sound is still being produced in all directions. But this, as it's moving this way, the sound waves spreading out this side, those waves start to compress. All right, because, so the motion of the car causes the sound waves to move, but the direction it's traveling, they condense, they shorten. So these waves now are shorter here. So if I were to, so we have shorter waves. They're closer together. The shorter wavelengths, higher frequency. Okay, and over here, they're longer. Longer wavelengths on this side. So if the police car is going toward us, if we're the X going toward us, we are going to experience those high frequency sound waves. That's a high pitch, so that siren then gets higher. It's like, so it's like that higher pitch going toward us, because the sound waves are compressed going toward us. If we, however, if we were here, so this X, and the car is going away from us, we are going to hear these waves instead. So we're going to pick up the longer waves, longer wavelengths, which is lower pitch. So this is called the Doppler effect. And it's really a perceived change in the frequency of waves based on the location of the observer and the object. Right, so if it's going away, you're going to experience the lower frequency, longer wavelengths sound. And this, think of this now, since light and sound, they both travel in waves. We use this if we look at stars. So if stars are moving toward us, the wavelengths are going to be getting shorter. So in stars, though, we're not going to hear the stars. We'll see a color shift. And the color shift we'll see is called the blue shift, because the blue light has shorter wavelengths. It's like this police car going toward us. However, the star is going away from us, and this is what we're mainly noticing in most of the stars, longer wavelength of light. So we're seeing that over time, we are noticing a longer visible wavelength. So the stars are shifting toward the longer wavelength. They're shifting toward the red side. So it's called the red shift. So that indicates they're going away from us. And if we know this, on most of the stars are going away, it's an indication that the universe is expanding. They're moving away. But how do we know this? It's the same thing we use when we figure out, is the siren coming our way? Is the police car coming this direction? Do I need to pull over? You know, I mean, you hear an ambulance coming, you want to know if you need to get off the road. So we can do that. We can detect that from the pitch, the sound it's producing. The high pitch, it's coming toward us. The lower pitch going away. It's called, do this, Doppler effect. So the Doppler effect is really just a perceived change in a wave's frequency due to the motion of the object producing the waves and the position of the observer. So it all is relative. It depends on the position of the observer.